Welcome to Study Loop.
This is the answer to Chapter 22, problem number 14, from the Smith Organic Chemistry textbook. This problem is asking us to treat benzoic anhydride, pictured here at the top, with 4 different reagents and to predict the products. And so the thing to remember here when trying to solve this problem is you have to remember how carbonyls typically react. And any of these carbonyl compounds, these carboxylic acid derivatives that we've been looking at in this chapter, are going to react in the same way. The carbon-oxygen double bond, and then especially the presence of an additional electronegative atom attached to that carbonyl carbon, is going to make the carbonyl carbon very electrophilic. And so these reactions will typically proceed by nucleophilic attack on that carbonyl carbon, which is an electrophile, formation of a tetrahedral intermediate, and then departure of the best leaving group. And so an anhydride is no different. The nucleophile will attack at one of the carbonyl carbons. So fortunately, in this example, we have an anhydride that is not a mixed anhydride. Both sides of the anhydride are the same, and so we don't have to think about which side might be more reactive. We can, safely assume that the reaction happens at either carbonyl, and it's fine because they're both the same. And so for A, water is our nucleophile, so water will attack. The tetrahedral intermediate will form. The anhydride bond will break, but we're actually left with 2 carboxylic acids. The reason being one half of the anhydride, wherever the water attacked, obviously will have this OH substituent because the H2O added there. The other half that left took the oxygen with it, and it'll pick up a proton either from the H2O that added here or just from other H2Os in the solution. And so we actually just get identical benzoic acids here. Okay, so then for B, again, methanol is going to be our nucleophile. So methanol will attack the carbonyl, will form the tetrahedral intermediate, pardon me. The anhydride will split, and so we'll end up with one half of the anhydride, wherever the methanol attacked, will have the methyl ester. And then again, the other side will be the carboxylic acid because it'll leave with just the 2 oxygens and no hydrogen, and it'll pick a hydrogen up from either the hydrogen that was on the methanol or just from another methanol that's in solution. So the only thing that really changes when we're looking at these nitrogen nucleophiles in C and D is that rather than picking up the hydrogen from the nitrogen nucleophile or from another nitrogen base in the solution, we're just going to form the salt. So NH3 is our nucleophile in C. It attacks, tetrahedral intermediate forms, the anhydride splits, and we're left with the amide on the one side. And then the other side, we're going to have, again, the deprotonated oxygen, but it will actually form a salt with this nitrogen. So the nitrogen, the ammonia, will pick up the proton that's running through the solution, running loose in the solution. The ammonia will pick it up and form the ammonium ion, and that will complex with the benzoate ion that we formed. And so again, we see the same thing for D, probably a little less reactive since there's the 2 methyl groups, but still reactive enough. So we get very similar products as to C. We get the amide for one side of the anhydride, and the other side forms the salt with the protonated dimethylamine. And so that's a pretty good overview of the reactivity of these anhydrides, and that is the answer to Chapter 22, problem number 14.